thank you everyone for coming today. It's great to see so many friendly faces. I'm really excited to talk about my PhD work on algorithms for black box safety validation. So automation promises to improve both safety and efficiency in a variety of domains. And in fact, it's already done so in the field of aviation. So in 1956, the US experienced its first commercial mid-air collision, and it resulted in more than 100 passenger deaths. This tragic event spurred the research into the collision avoidance systems that are on board all commercial aircraft today. And they're actually thought to improve the safety of flying by a factor of between 3 and 5. So as our airspaces become more diverse and denser, we need to develop new collision avoidance systems to deal with these new issues. Another field that could really benefit is the field of transportation. So currently, driving accidents kill more than 1 million people every year. And as many as 94% of all accidents are actually just due to driver error. So if we can introduce automation for vehicles, then we could potentially save a lot of lives and have safer roads. So bringing autonomy into safety critical domains is not without its risks. And this was demonstrated in March of 2018 when an automated test vehicle operating in self-drive mode struck and killed Elaine Herzberg as she crossed the street. This was the first recorded incidence of a pedestrian fatality due to a self-driving car, and it really drove home the risks associated with deploying these systems. So what we need to do is establish rigorous safety requirements, which will include both safe design of these systems and thorough testing. So in order to understand how safety is incorporated into the design of an autonomous system, we have to understand how such systems are built. So I've modeled the autonomous system design cycle here, and it starts with the definition of some number of requirements. So this is what we want our system to do. And we'd like to identify what safety features it should have, as well as identify any dangerous states we wish to avoid. Then we'll undertake some design effort. And nowadays, this typically involves a lot of machine learning, as well as other engineering effort, in order to develop a prototype of the system. Then once we have this prototype in hand, we're going to want to generate a bunch of tests for it. So this may be unit tests or component tests, as well as full integration tests that test the system's safety as a whole. And we can use those tests to evaluate the performance of the system, either by computing a probability that the system fails or how severely it fails. Then we can take these failures and try to understand what went wrong with our system. So this can be done through failure classification or root cause analysis. And once we've done that, it may show us that we have to define more requirements or put in more engineering effort. And so we iterate on this process until we have a sufficiently robust system. So the portion of this design cycle that I like to focus on is this portion here, which I broadly categorize as safety validation. And that's what I'll be talking about for the remainder of this talk. So there are a couple different approaches to safety validation. The first and perhaps the most obvious is real world testing. So here we would take a prototype of our system and let it operate in real world conditions. And this can be really great because it shows us how our actual system will behave in its actual environmental conditions, but it's expensive in both time and money, and it can be risky if we don't already have a safe system. So in order to reduce these costs and the risk, we typically turn towards simulation. And in particular, we design challenging scenarios for our autonomous system, and we can design these scenarios using the expert knowledge we have of the particular domain in which it's operating in. Now, the problem with this approach is because we're designing these scenarios by hand, we can miss the sort of unexpected or emergent failures that can occur with very complex systems. So one way of avoiding missing unexpected failures is using approaches from formal verification. So in formal verification, we actually are able to construct proofs of the safety of our system, and we therefore eliminate any risk of missing particular edge cases. The problem is, though, that these approaches don't typically scale to the very complex and uncertain domains that we care about, like autonomous driving. So the approach that has been developed further for these systems, and the one that I'll be focusing on, is black box sampling techniques. So here we assume that we have no knowledge of how the system was designed, and we put it in sort of randomized environmental scenarios and then determine how well our system performs. And the benefit of this is that it scales to very complex systems, and then we can apply adaptive sampling and machine learning techniques to uncover unexpected failures. There are a couple of challenges associated with black box sampling techniques. The first and foremost is that we need to adequately represent both our system and the environment in which it operates. So this typically requires a simulator that is high fidelity enough to capture the things that we care about. And then the other challenges are that if we already have a very safe system, then failure events are going to be rare and very difficult to find. Secondarily, because we're not testing any specific component or behavior of our system, it can be difficult to interpret what it was about the environment that caused a failure. And then lastly, such simulators that we use can be very expensive to run. And so it can be computationally burdensome to have to run these black box sampling techniques many different times. And so this brings me to the contributions I've made and we'll be talking about for the remainder of the talk. So first, in order to help find the most relevant failures of a system, I developed a scalable approach to trying to learn the distribution over failures. In order to improve the interpretability of black box sampling algorithms, I developed a technique that learns failure descriptions that can be actually understood by humans. And in order to improve the computational efficiency of black box sampling algorithms, I developed a method that shares knowledge between safety validation tasks when we're validating related systems. So with that, I'm going to jump into the first contribution. But first, I'm going to talk about how we actually formulate this problem of black box safety validation. So the problem is depicted by this diagram here. We have a black box system that's operating in some environment, so it can take actions in that environment after receiving some observations. At the same time, we have an adversary that can perturb the environment through some disturbance X after observing the true state of the environment. So to introduce a little bit of notation, we call a sequence of disturbances a disturbance trajectory. And this disturbance trajectory will induce a state trajectory mediated by this function f. And this function f captures the behavior of the system as well as the dynamics of the environment. Then we may have a model over the disturbances. So this captures basically the distribution over disturbances that we would see in our environment, basically determining which disturbances we're actually likely to encounter. And we can have that model over the entire trajectory of disturbances or over each given disturbance given the current state of the environment. Then we have a safety specification psi. This just describes the behavior that we hope our system abides by. And we say that a system fails if the sequence of states that's induced by this disturbance trajectory violates that safety specification. So this can be a little bit abstract. So in order to make it a little more concrete, I'm going to introduce this autonomous driving example. So here we have the system under test is an autonomous vehicle that's controlled by the intelligent driver model with some additional logic to help it navigate intersections and avoid collisions. The environment is a driving simulator that will include the road geometry, the position and velocity of the other agents, as well as the dynamics of motion. And then the adversary can control the other agents on the road. So it can control things like their motion, their intention to turn or go straight, as well as the use of a turn signal. It can also control things like the noise and the perception system of the ego vehicle, as well as things like the weather conditions or road conditions. And then we define a failure to be anytime our ego vehicle collides with another agent on the road. So there are a couple different schools of thought when it comes to trying to uncover failures of an autonomous system. And to illustrate these different schools of thought, I'm going to use this really simple safety validation problem. So here we have an agent, this little blue circle, that's trying to reach one of these green squares, and it fails if it lands in one of these red squares. So in general, it has control over the next square that it moves to, but occasionally a disturbance will kick it off course. So the first approach that people have taken to finding failures is called falsification. And so this is basically just trying to uncover any sequence of disturbances that would lead our system to a failure. And so an example might look like the trajectory that's shown here. The problem is, though, that it doesn't include the probability of the disturbances. So this kind of wild trajectory is probably not likely to occur when we actually run our agent in the real world. So another approach is most likely failure analysis. So here we try to maximize the probability of a given failure trajectory, and then we end up with much more relevant failure examples. So here we might have a trajectory where the agent is trying to reach this green square up here, and at the last second gets kicked into a failure mode here. And this is the type of failure that we would actually expect to see when we run simulations of this. But I would argue that this approach, although effective, can oftentimes miss different, more diverse failure modes. So for example, there's a possible failure mode down here, and it's possible that the agent doesn't take this exact trajectory to find failure. So the approach that I advocate for is to try to learn the distribution over failures. So what this means is that we want to try to sample all the different possible failures with probability proportional to the likelihood that they would actually occur. And so we've sampled 100 failures from the distribution over failures, and we see that many of them do indeed follow this most likely failure trajectory, but they also have a lot of variation and include this secondary failure mode. So that was the goal for this first approach, was to approximate this distribution over failures. Now, previous work that has tried to do this broadly comes under the category of importance sampling approaches. So things like the cross-entropy method and multi-level splitting have been used to try to learn this distribution. And the problem with these approaches is that they often require optimization over the full disturbance trajectory, which can be very high dimensional and challenging to optimize over. And they don't have a natural way of incorporating the state of the environment into the choice of the disturbance. So if you have random state transitions or you have different state initial conditions, then these approaches aren't as effective. So what we asked is, could we learn a disturbance policy? And what I mean by that is a distribution over disturbances that depends upon the current state that we're in. And then we could use that policy to roll out and find example failures. So it turns out that if we assume that our system is Markov and deterministic, then this disturbance policy exactly reproduces the distribution over failures. So to give you some intuition as to why this might be the case, we can look at the various terms. So this first term here is just our model of how likely a given disturbance is. And so what we're saying here is that all else being equal, the disturbances that are actually more likely to occur should be sampled more frequently. And the second term here is the probability that the system fails from being in state S and applying disturbance X. And so what this says is the more likely a disturbance is to cause a failure, the more likely it should be to be sampled. And then we have a normalization factor as well to keep this a distribution. So what we've done is turn this sampling problem into an estimation problem where we're trying to estimate the probability of failure at each state. And so in order to do this, we can leverage an observation from the model checking community. And that observation is that the probability of failure satisfies this recursive relationship. So it's 1 if the state that we're currently in is already a failure. It's 0 if the state we're in ends the episode that we're in, but is not a failure. And otherwise, it's going to be just a weighted sum of the probability of the possible disturbances we could choose and the associated probability of failure from that next state. So for those of you who are familiar with reinforcement learning, this type of recursive relationship should look really familiar. And in fact, we can use similar techniques such as the deep Q network approach to represent the failure probability as a neural network and then train it towards the satisfaction of this recursive equation. But because we're trying to estimate the probability of failure in this case, we can't just use the typical mean squared error loss function because the probability of failure is typically a very, very small number close to 0. So instead, we use the mean squared log error, which just penalizes the difference in the order of magnitude of the estimate of the probability of failure. So we can see how well this works by looking at the probability of failure of that grid world example that I've been talking about. So we got the ground truth by using just a dynamic programming solution to this problem. And the color represents the probability of failure for being in that state. So our neural network is able to capture all the major features of this probability of failure landscape. And it actually does so over about 30 orders of magnitude over the probability of failure. So this bodes well for being able to represent relatively complex landscapes. But typically we don't have the ground truth. So how do we actually evaluate the effect, how well our approach is doing? We can do this by actually using samples. So what we do is we take our estimate of the probability of failure and plug it into this disturbance policy. Then we can simulate random rollouts of our agent in the world, and then use those rollouts to try to look at how good we're doing. And some of the metrics that we use to evaluate this are the rate of failure. So how many of those episodes actually ended up in a failure state? What is the likelihood of those failure trajectories? So here, if we've done our job, the relative likelihood of the failure trajectories should be large. So we're only using rare disturbances when we absolutely have to. And then we should be able to take these samples and use them to estimate the probability of failure. And the number of samples we need to do that should be smaller if our approach is effective. So in order to actually test this approach in a more realistic setting, we're going to use this driving scenario that I already introduced. So we have the ego vehicle trying to take a left turn with a single adversary on the road to the left. So this adversary is nominally controlled by the intelligent driver model, but it can be perturbed by the adversary. And those disturbances that can be applied can either slow the vehicle down, speed it up, or it can toggle its intention to make a right turn, as well as toggle the use of a turn signal. So the approaches we're going to compare is our approach, where we estimate the probability of failure using a neural network, as well as estimate it using a local approximation dynamic programming. And we're going to compare that to Monte Carlo rollouts of the simulation. So this is where we just take each disturbance, we sample it with its true probability. Then we have a technique where we sample each disturbance with equal probability. And then we a third baseline is the cross-entropy method, where we actually optimize this distribution and use it to estimate the probability of failure. So some results from that work, you'll see some example failures playing in the top left. But if we want to look at the quantitative analysis here, we can first look at the failure rate. And we see that both of our approaches have a significantly higher rate of failures than the baselines. But that would be meaningless if it didn't also produce trajectories that also had high likelihoods. And we see that the likelihood of the trajectories from our approach is quite similar to the best possible likelihood, which is those coming from the Monte Carlo approach. Then we can use these samples to estimate the probability of failure. So this plot shows our estimate versus the number of samples we used. And our approaches in purple and tan are able to get a high quality estimate with orders of magnitude fewer samples than these baseline approaches. So this looks really great, but the biggest problem is that our approach has introduced this dependence upon the state of the environment. And if the state space gets really large, then this could be a serious problem. So one of the challenges is how do we scale this up to environments that have very large state spaces? So to investigate this problem, we made a slight modification to our simulation that includes 3 additional adversarial vehicles. And the state space of this problem, it actually gets exponentially larger with the number of agents that are interacting. So this can become completely intractable for example, for the dynamic programming approach that we used before. So in order to make this more tractable, we took inspiration from some previous work done by Bhutan in 2019, where they decomposed a driving scenario into pairwise interactions between the other agents on the road and the ego vehicle. In that work, they used that decomposition to actually train the driving agent itself. But we had the idea of using a similar approach to actually train the adversary to find failures in this way. So we split up the problem into these pairwise interactions. And for each subproblem, we solve for the probability of failure for each combination of states. We then use a transfer learning approach called attend, adapt, and transfer that estimates the probability of failure as a weighted combination of these subproblem estimates. And then using rollouts of the full simulation with all of the different agents interacting, we learn a series of attention weights to combine these estimates into a final estimate. And so the results of that are shown here. So again, we have some failure examples playing in the top left. And we see that the rate of failures that we find in this case is about 3 times larger than the best baselines. But more importantly is we have a significantly higher log likelihood of those trajectories using our approach. And that translates into an effective estimate of the probability of failure with significantly fewer samples. And in this case, only the cross-entropy method was able to eventually get a decent estimate. Okay, so with that, I'm going to give a quick summary of this contribution. So we are approximating the distribution over failures in order to improve both the failure diversity as well as allow for better estimation of the probability of failure. We used a policy-based approach that sampled disturbances with probability proportional to the failure probability. And then in order to scale it to large state spaces, we used a state space decomposition and a weighted recombination technique. And this approach increased both the failure rate, the log likelihood of the trajectories, while reducing the number of samples we needed to estimate the probability of failure. So a couple limitations of this approach. Currently, we don't have a good characterization of the statistical guarantees that we could make about the probability of failure estimates. So some more work needs to go into that. And currently, we only handle discrete disturbances. So more work needs to be done to expand this to continuous domains. Okay, so with that, I'm going to move on to the second contribution, which is to improve the interpretability of safety validation black box algorithms by learning failure descriptions. And so a little motivation for this. This image here, it depicts a sample failure trajectory from an aircraft collision avoidance system where 2 aircraft are having a close encounter. And what we see is that these trajectories that we find are incredibly high dimensional. So I'm not asking you to understand what's going on here. I'm just demonstrating that a single failure example can produce a ton of data. So we have 4 different variables here for 2 different aircraft happening over time. So it's not clear what it was about these trajectories that actually led to a failure. So what features are relevant to this failure? So existing approaches that try to tackle this problem use techniques from interpretable classification. So for example, Lee in 2018 used decision trees with temporal logic specifications to categorize different failure trajectories into various understandable failure modes. Vasquez and Chenlet in 2017 did a similar approach where they clustered different trajectories based on a specification that they defined. And so these approaches do a good job of identifying certain features that distinguish different failure modes, but doesn't mean that they can capture the entirety of what it means to cause a failure. And so the goal of this work was to try to find an interpretable description of disturbance trajectories that cause a failure. And so the falsification problem looks like this. We're trying to find a description psi, or phi, excuse me, such that any disturbance trajectory that satisfies phi implies that the system fails. And so we can turn this into a most likely failure analysis problem by performing a maximization over the failure descriptions for the expectation of the probability of the failure trajectories, subject to the constraint that those trajectories end in failure. And so some of the questions that we had to answer while designing this algorithm are: what language are we going to use to describe these failures? How do we actually sample disturbance trajectories that satisfy a given failure description? What optimization strategy could we use to optimize these expressions? And then what cost function would lead us to maximizing both the probability of the trajectory as well as satisfying this constraint? So we took some inspiration from those previous works that I mentioned and settled on using signal temporal logic as our language of specification. So temporal logic is basically a logical language that includes the traditional logical operators like and, or, and not, but also includes these time extended operators such as always and eventually. So for example, we may have the specification always between time steps t1 and t2, the variable x is greater than 0. So it turns out that these expressions can be represented in tree-like structures, and tree-like structures are optimized using a technique called genetic programming. So genetic programming draws its inspiration from biological evolution, where we maintain a population of trees, and then we evolve them over time using simulated reproduction with crossover as well as mutation. So we need a cost function in order to guide this evolutionary process. And the cost function we settle it is on is given here. It looks relatively complicated, but it's actually pretty straightforward. So we are basically trying to estimate the probability of trajectories that satisfy a given specification multiplied by an indicator function of whether or not that trajectory ended in failure. So if a given description produces trajectories that never end in failure, then the cost will be 0. And if we have a description that does produce failures, then the value of the cost function should be the average probability of those trajectories, or the negative of that. So the final piece of this is, how do we actually sample trajectories that satisfy a given specification? So the first thing we do is, given a specification, we sample a set of linear constraints that enforce that satisfaction. So in this example, we have the specification that always between time steps 1 and 20, x is less than 0.5. So we block out that region where x is greater than 0.5. And then we have and eventually between time steps 21 and 40, x is greater than 0.9. So here we take a random time point in that range and then block out the region where x is less than 0.9. Then we can sample our time series from our baseline distribution, satisfying those constraints, and we get a satisfying trajectory. So we can put this all together in this interpretable safety validation algorithm. So the first step is we sample a population of possible failure descriptions from the grammar that represents our signal temporal logic. Then for each of those specifications, we sample a bunch of trajectories that satisfy it, and we compute the average cost of those trajectories. Then if the average cost is less than some safety threshold, we can return our description confident that it does induce failures. Otherwise, we can perform the operations of genetic programming to evolve our population towards better and better descriptions. So we tested this approach on the same driving setup that you've seen previously, but the benefit of this approach is that it can more naturally handle continuous disturbances. So here we have distributions over the acceleration, as well as distributions over the perception noise of the ego vehicle. Okay, so here are some sample failure descriptions that were found. The first is the description always, the perturbation to the acceleration of the adversary is about 1 meter per second squared. And so in this case, the ego vehicle thinks it has enough time to take this left turn, but due to this extra acceleration, it induces a collision. Then we have a description that eventually between time steps 0 in the first 0.3 seconds of the simulation, the adversary toggles its turn signal. So in this case, the adversary turns its turn signal on, making the system under test think that it's turning right when in fact it continues on straight, causing a collision. And then a third description involves both the toggling of a turn signal as well as a slowdown in the early part of the simulation, leading to another failure mode. So what we can do with these failure descriptions is not only understand them, but use them to produce many different failure examples. And it turns out that the rate of failures that it produces is often very high because these descriptions are good descriptions of what caused the failure. So compared to the cross-entropy method, we see at least an order of magnitude increase in the failure rate. And additionally, the failure trajectories that we find have large log likelihood because it's only constraining the most important parts of the disturbance trajectory in order to cause a failure. So as I said, we can also produce a variety of failure examples. So we've sampled 10 random trajectories that satisfy this description and plotted them in this velocity versus position diagram. So we see that initially they share a similar attribute, which is that they have this dramatic slowdown at the beginning, but then they're allowed to evolve according to the true distribution over disturbances. And we end up with 10 sort of diverse different failure modes. So a brief summary of that contribution. I argued that black box safety validation algorithms, because they produce high dimensional failures, they may be difficult to interpret. And existing techniques rely only on classification and don't actually find full failure descriptions. So our technique actually directly looks for these failure descriptions. And it turns out that this technique is really similar in spirit to the approaches that are used for interpretable reinforcement learning. And this description can be used to reduce the dimensionality of these failures for ease of interpretability, as well as produce failure examples, all with relatively high likelihood. So a few limitations of this approach. The first and I think most obvious is that a failure description must actually exist for our algorithm to find it. So if there isn't a somewhat simple description of what causes a failure, then this algorithm won't work. And also genetic programming, it can work effectively for these types of approaches, but has no convergence guarantee. So if we don't find a failure, then we can't necessarily be confident that no failure exists. So with that, I'm going to move into my third and final contribution, which was to improve the computational efficiency of black box sampling algorithms using a method that shares knowledge when we go to validate related systems. So what are the scenarios in which different systems might be related that we're trying to validate? So the first is that of a system that learns over time. So in this setting, you can imagine you're an autonomous vehicle company developing a fleet of autonomous vehicles, and you may make updates to your system every week or every 2 weeks. And every time you do that, you want to validate the safety of your system. This is to make sure that you've squashed any bugs that were already there, as well as not introduced new bugs. Another scenario that we might care about is that of the validation of many related yet similar systems. So here I imagine if you're a third-party agency that's trying to validate the safety of various autonomous vehicles coming from a variety of different companies, you should be able to use what you learn on the validation of one system and apply it to other systems. In this setting though, the behaviors of these systems may be pretty different from one another. So what we propose to do is to apply a transfer learning technique to improve both the efficiency and performance of safety validation algorithms. So a brief primer on transfer learning. We assume that we have a series of tasks that we're solving and that we've solved some number of them and have the corresponding solutions. So then we use those previous solutions to try to solve the next task with the goal of either solving that task more quickly or to a higher level of performance. So in safety validation, each task would be perhaps a Markov decision process that varied in its transition function, which captures the behavior of the system as well as the environment. So if the system behavior changes, then the transition function should change. But we assume that we have the same state space and the same space of disturbances. And then in our case, we're going to be working in the setting where the solution is the action value function for the given MDP. And this just characterizes which disturbances we should choose in order to find the most likely failure. So although there hasn't really been a lot of work on solving this specific problem, I see it most similar to the work done in adversarial reinforcement learning, where we actually train both the system and the adversary simultaneously. And so here, the adversary is going to be kind of continually updating in order to address the failures of the system. And these techniques are typically effective because the adversary only has to deal with very small changes in the system. Whereas the setting we're talking about the system is going to undergo pretty dramatic shifts between changes. So the approach that we proposed was to retain and transfer knowledge using action value functions. And so again, we're applying the attend, adapt, and transfer algorithm, which combines knowledge using a learned set of attention weights. So we take our action value function and estimate it as a weighted sum of the previous solution's action value function, as well as a solution that we're going to be learning from scratch. And then the weights that we use to combine these estimates depend upon the state of the system and then can get learned over time. So it turns out that this expression can really be easily captured as a neural network architecture. So this architecture takes as input the state. It passes it through this baseline network that we learned from scratch, as well as all the previous solutions that we have. And this gives us estimates of the Q values of each of those. Simultaneously, it's passed through the attention network to get a set of weights. These weights are combined with the values to get our final estimate. And then we can use backpropagation to train the parameters of this network. So when we were experimenting with this architecture, we found that it performed very poorly if we we had minor transformations of the state space or the disturbance space. So what we proposed to do was to introduce a little more flexibility into this architecture by allowing for linear state and disturbance space transformations that happen before and after the state is passed through the solutions. And so this allows us to kind of reuse more of the previous solutions. So in order to test this approach, we use the following experimental setup. Here we have an autonomous vehicle that approaches a crosswalk that a pedestrian is trying to cross. And we've artificially hindered our autonomous vehicle with a blind spot in a particular angle with a particular angular width. And so we simulate this setting of the learning system by, on each successive task, narrowing that width of the blind spot. So its performance improves over time. And then in the comparable system setting, we have each task have a vehicle with a blind spot in a different direction with a different angular width. So the failure modes should be rather distinct between these systems. So then the algorithms that we try to compare. So first we want to capture this idea of kind of a slowly changing adversary. And so we used a fine tuning approach where we just simply use the action value function of the previous solution, freeze all but the last layer, and then train that layer to try to solve the current task. Then we use the traditional attend, adapt, and transfer architecture, as well as the architecture with these state and action value transformations. And in order to compare these different algorithms, we use the following transfer learning metrics. So this plot here shows the performance of two hypothetical algorithms versus the number of training steps they've had. So in blue, we have the algorithm that learned from scratch, and in green, we have a hypothetical algorithm that learned with some amount of transfer. So the metrics that we can look at first is the jumpstart performance. So this is how much better is our transfer learning algorithm right out of the gate before no extra learning has been done. Then we can look at the steps to threshold. This is basically how many training steps are required to reach a certain level of performance. And then lastly, we can look at the final performance, which is just compares the difference in the best performance seen by both algorithms. And we normalize these metrics to the algorithm that learned from scratch. So a couple of results. So first from the learning system, these plots here on the x-axis show the task that we're solving, the task iteration that we're solving, and the y-axis is the various performance metrics. So we see that initially in the learning system, we have high jumpstart performance because failures that are found in early tasks are very applicable to the previous task. But as the agent gets better over time, there's no longer much applicability between the failure modes that were found. We can look at the final performance, and we see that for the A2T algorithm, which is shown in blue and green, that we see a significant improvement in final performance compared to the fine-tuning baseline. And then lastly, we can look at how many steps were required to reach basically the optimal performance of the from scratch algorithm. And both of the A2T architectures required much fewer time steps than the from scratch algorithm, whereas the fine tuning approach frequently did not reach even that level of performance. And when it did, it often took longer than the from scratch algorithm. So in the comparable system setting, we see some slightly different trends. First, the jumpstart performance starts low, but actually improves as the number of tasks that we've seen. And this is probably because the more tasks that we've seen, the more likely it is that we encounter a new task that's similar to one of the old tasks. We see a modest improvement in the final performance in this setting, but the biggest upshot is, again, the number of steps required to reach the same level of performance as the from scratch algorithm. In this case, the use of these state and action value transformations after about 5 tasks have been seen can dramatically improve the performance of the A2T algorithm. So with that, I'm going to summarize this final contribution. So I suggested that iterative safety validation can benefit from the use of knowledge transfer. And we identified 2 distinct relationships between systems, that of a learning system and then that of comparable systems. We showed that fine-tuning can often fail to improve the learning performance and often hinder it. And that A2T can be applied for significant efficiency gains. And then when systems exhibit really distinct behavior, we can incorporate these state and action transformations to try to improve generalizability. So some limitations of this approach. The biggest one, I think, is that it requires the storage of all of our past solutions. So if we're doing hundreds or thousands of safety validation trials, then we're going to have to store these networks along the way, and that can be very cumbersome. And then as with any transfer learning algorithm, it might be the case that what we learned on previous tasks actually hinders the validation on new tasks, especially if we've kind of changed the behavior dramatically. So with that, I'm going to provide a brief conclusion. So I argued at the beginning of this that black box safety validation is both an effective and scalable approach to trying to validate the safety of the autonomous systems of the future. And I provided a general formulation of the black box safety validation approach. And then in order to increase failure rate and improve the probability of estimation, I introduced a technique for learning the distribution over failures. In order to develop interpretable failure descriptions, we developed a technique that can look for these failure descriptions, which provided insight into the cause of certain failures, as well as the ability to sample failure examples. And then we applied efficient iterative safety validation using knowledge transfer and improved the final performance and reduced the needed number of samples for these safety validation algorithms. So in addition to addressing some of the limitations that I've already highlighted, I think some directions in this general line of work that are going to be really important going forward are the validation and verification of image-based controllers. So these are going to be techniques that specifically work on autonomous systems that use cameras for input, because this is going to be very common going forward with autonomous vehicles. Another interesting line of inquiry would be analyzing the coverage of our testing. So basically answering the question, when have I done enough testing? And then lastly, how do we actually take these failure examples that we found and use them to improve the underlying system? So during my time at Stanford, I've had a couple of publications. The 3 that I've highlighted here are the 3 that correspond to the 3 contributions I spoke about today. If you're curious about the whole wide world of safety validation algorithms for black box systems, I wrote a survey paper, which is currently up on arXiv,